V is a multiple of live streaming is a V is a multiple of A. Denoted by symbols A by B. Now, if A does not divide B, if A does not divide B, does not divide B, then write then write then write A by B, yeah, and B are associates, and B are associate. Associate. B are associate. And is denoted by is denoted by denoted by A similar B, A similar B. Next definition. Definition. That P is non-zero, let P is non-zero, P is non-zero, P is non-zero, and non-unit in integral domain are non-unit in integral domain. Integral domain. Integral domain are then P is said to be prime element in R. Said to be prime element in R. Prime element in R. For any, for all A comma B belongs to capital R. P divides AB. P divides AB. That implies either P divides A or either P divides A or P divides B. P divides second. P is said to be irreducible element. Said to be irreducible element. Reducible element. If in R A comma B belongs to comma belongs to P equal to AB. Either A Either A is a unit or B is a unit. Either A is a unit or B is a unit, a unit. In other words, P is called irreducible. P cannot be written as product of two non-unit symbols. So using these definitions, we'll solve a theorem, prove a theorem. Page number 237, important for 10 marks. Theorem, statement. Prove that or show that every prime element in an integral domain, every prime element in a prime element in an integral domain integral domain integral domain is irreducible is irreducible irreducible irreducible. Then the converse is not true in general. Converse is not true in general. In general. Page number 238. Proof. Proof. Let P be a prime element in an integral domain. Let P be a prime element in integral domain integral domain. Then by definition, P is non-zero and non-unit in R. Then by definition, PEFM is definition. P is non-zero and non-unitary. Non-unit in R. Non-unit in R. Non-unit in R. Let A and B any elements of R. Let A and B any elements in R. Any elements in R. Any elements in R. Such that P equal to AB. The ST means such that P equal to AB. Okay. Then P divides AB. Then P divides AB, then P divides AB. Since P is prime, since P is prime, P is prime, since P is prime, we have either P divides A or P divides B. We have either P divides P divides P divides A or P divides P divides B. P divides B. If P divides A, then P are equal to A. If P divides A, P divides A, then P are equal to A. P are equal to A. P are equal to A. For R belongs to capital R. And therefore P equal to AB. So P equal to AB. P equal to AB. P equal to AB. That equal to PR into B, we can write that equal to P into within the bracket RB, we can write. Since R is integral domain and P is not equal to 0, since R is integral domain, integral domain, integral domain, R is integral domain, and P is not equal to 0. And P is not equal to 0. We get that we get that 1 equal to RB, 1 equal to RB. That is B is unit. That means B is unit. B is unit. B is unit. B is unit. Similarly, we can prove that. Similarly, we can prove that. Similarly, we can prove that P divides B, then A is a unit. If P divides B, then A is a unit. Unit is a unit. P there, thus P is irreducible. Thus P is irreducible. Then P is irreducible. P is irreducible. This completes the proof, hence proof. Hence proof. Okay, next. One more important thing is page number 239. Page number 239. This is also for important for 10 minutes. 10 minutes. So theorem. Theorem. If R be a principal ideal domain, principal ideal domain, prove that. Question formation is prove that or show that domain and P belongs to R. P belongs to R. Then P is prime. Then P is prime. Then P is prime. If and only if P is irreducible. If and only if P is irreducible. Irreducible. If and only if P is irreducible. Proof. Proof. That P is prime. P is irreducible. If P is prime, P is prime, P is prime, P is irreducible. Just now only proof. P is irreducible. P is irreducible. Let P is neither zero nor unit. Let P is neither zero nor unit. Neither zero nor a unit. Unit. Let AB belongs to let AB belongs to R. Belongs to R. Such that P divides AB. ST means such that P divides AB. We have to prove that P divides A. We have to prove that. Have to prove that P divides A or P divides B. P divides. Consider L equal. Consider I equal. Consider I equal. Consider I equal. Consider I equal. PR plus AS. PR plus AS. PR plus AS. Plus AS. PR plus AS. Divides R. S belongs to R. S belongs to R. Then I is an ideal of R. Then I is an ideal of R. Ideal of R. Ideal of R. Since R is a principal ideal domain, I is a principal ideal domain. Ideal domain. For ideal domain. Here exists C belongs to I. C belongs to I. Since that I equal to CR. That's that. I equal to CI. I equal to CR. Since P comma A belongs to I. P comma A belongs to I. Belongs to I. The registry XY belongs to R. The XY belongs to R. Such that. Such that. Such that. Such that. Such that. A equal to CR. A equal to CR. Now, since P comma A belongs to such that P equal to CX, such that P equal to CX, and A equal to CY, and A equal to CY. Since P is irreducible, since P is irreducible, since P is irreducible, either C is a unit, C is a unit, that C is a unit, or X is a unit, X is unit, unit. Okay. If X is a unit, then PA inverse. If X is a unit, X is a unit, then PX inverse, PX inverse equal to CX into X inverse. And hence, and hence, and hence, A equal to CY, A equal to CY, A equal to CY. PX inverse Y, that equal to Y of X inverse Y, X inverse Y. So that P divides Y, so that P divides Y. If C is the unit, C is a unit, then I equal to, C into C inverse that belongs to I. And hence I equal to, and hence I equal to PR plus AX, PR plus AX, PR plus AX, PR plus AS, not X. Yes, AS for all R comma S belongs to capital R. B equal to, and B equal to VPR plus BAS. VPR plus BAS. If you take P is common, BR plus V2 equal to P for the PBR plus PS. B equal to BAR plus BAS. If you take B is common, BR plus AS we can take. We take B is common. PR plus AS. PR plus AS. Where AB equal to PT. That means that implies P you are taking means PR plus TS, PR plus TS. That means here AB equal to PT, AB equal to PT, equal to PT. This is possible, then P divides AB. This is possible. P divides AB. P divides AB. So that P divides P. So that P divides B. P divides B. Therefore, P divides A or P divides B. Then P is a prime. Therefore, P divides A. P divides A. Or P divides B. P divides B. Thus P is prime. Hence proof. Hence proof. Important for 10 minutes. Next. Page number 238. 238. Example sum. Example 4.2.4. 4.2.4. 4 marks for 10 minutes. 10 minutes question. 10 minutes. Next. Unit factorization person. Next. Worked out examples. Page number 243. Page number 243. Exercise problem. 4.4.1. 4.1. 12.4.2. Next. 12.4.4. In these three theorems, one theorem 10 minutes. 4 marks. One theorem is 10 minutes. For 10 minutes question. 10 minutes. Okay. Now we'll discuss most important theorem for 20 marks. That is unique factorization domain. Unique factorization domain. Definition. Unique domain. Unique factorization. Unique factorization domain. Definition. 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 An integral domain R an integral domain R, the integral domain R is said to be unique factorization domain is said to be is said to be is said to be unique factorization domain domain yeah, factorization domain. If it satisfies the following, if it satisfies following, factors following. Next, first, any non-zero element in R, any non-zero element in R, zero element in R is either a unit, is either a unit, page number 240, yes, 240, is either a unit or can be expressed as a product of, can be expressed, can be expressed, can be expressed as a product of finite number, as a product of finite number, a product of finite number, is a product of finite number of irreducible elements in R. Irreducible, irreducible elements in R. Irreducible elements in R. If P1, P2, if P1, P2, Pn, P1, P2, etc., Pn, that equal to Q1, Q2, etc., Qn, where Pi's and Qis are irreducible, where Pi's, where I equal to 1 to n, meaning Pi's, Pi's, and Qis are, Qis are irreducible, IRRE, DU, CI, BLE, irreducible, then n equal to m, then n equal to m. This is P1, P2, etc. Pn. This is Q1, Q2, Qm. This is. That's why n equal to reducible. Well, then n equal to n. Then n equal to m. N equal to and each PI is an associate. Then each PI is associate. Each PI is associate for some Q of some Q, some Q, some QJ. QJ, where J equal to 1 to that, and vice versa, and vice versa. Or SA, vice versa, means etc. The most important theorem, compulsory gunshot question, theorem for 20 marks. So sometimes they will give 20 marks, sometimes 10 marks also. Most important. Page number 240. Page number 240. Theorem. Every Euclid prove that or show that. Question formation is prove that or show that. Every Euclidean domain, every Euclidean domain, Euclidean domain, every Euclidean domain is a unique factorization domain. Unique factorization domain. Unique factorization domain. Unique factorization. So let R be a Euclidean domain. R be a Euclidean domain. Euclidean domain. Euclidean domain. With Euclidean map D. With Euclidean map D. So we have to prove that 1 and 2 in the definition are satisfied. We need to prove that. To prove that definition 1 and 2. Before we discuss it, that means part 1. 1 and 2 definition means definition 1 and 2. Prime element and irreducible element. Second definition we need to prove. Let P be a non-zero element in R. Let A be a non-zero element in R. Non-zero element. Non-zero element in R. Non-zero element in R. We use induction on D of A. We use induction. We use induction on D of A. On D of A. On D of A. On D of A. To prove that either A is, to prove that Either A is a unit, either A is a unit or A or A can be expressed, can be A can be expressed. Here only just now we discussed about factorization definitions, those only. Yeah. It can be expressed, expressed, expressed as product of finite numbers, as product of finite numbers, product of finite numbers of irreducible elements, irreducible elements, irreducible elements. Note that D of 1, that means D of 1 less than or equal to D of 1 is less than or equal to D of A, D of A. If D of A equal to D of 1, if D of A equal to D of 1, D of A equal to D of, then A is a unit, then A is unit, unit. Suppose let D of A is greater than D of 1. D of A is greater than D of 1. D of A equal to D of 1. And assume that 1 holds, and assume that assume that 1 holds for any non-zero element, non-zero element, any non-zero element, non-zero element x with non-zero element x with d of x is less than d of a. Yeah. So a is irreducible. Then we are through. If a is irreducible, a is irreducible, then we are through. We are through. We are through. Suppose a is not irreducible. Let a is not irreducible. Irreducible. A is not irreducible. Then A equal to BC. Then A equal to BC. For some non-units B and C. For some non-units B and C. B and C. B and C. B and C. In R, in R, we have in previous theorems, then we have D of B, D of B is less than D of B of C, D of C. That equal to D of A, equal to D of A. And D of C and A, and D of C, D of C less than D of BC, D of BC. That equals to D of A, D of A. Therefore, by induction hypothesis, so by induction hypothesis, we get B equal P1 from P2, P1, P2, etc. Pn. Then and C equal to Q1, Q2, etc. QEM. Here. PIs and RIs are irreducible, where PIs and RIs is equal to R1, R2, Rn, not Q. Zero down. Equal to R1, R2, etc. Rn. PIs and RIs are equal to PIs and RIs. RIs. Okay. PIs and RJs are irreducible. 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 Then A equal to BC. A equal to BC. That equal to P1, P2, etc. Pn into R1, R2, R1 into R2, R1, R2, etc. Rm, Rm, Rm. And therefore A is product of n. Therefore A is product of finite numbers, is a product of finite numbers, product of finite numbers of irreducible element, of irreducible element. Irreducible element. Part one is proved. Next, second one. Second. Let P1, P2, Pn equal to Q1, Q2, etc. Qm. Then Pi's, then Pi's, Qj's are irreducible in R, where Pi's and Qj's irreducible in R. Yeah, irreducible in R. Irreducible in R. Irreducible in R. Since R is a Euclidean domain. Since R is a Euclidean domain. Euclidean domain. Euclidean domain. Every irreducible element is a prime in R. Every irreducible element is prime number in R. Prime in R. And in particular, PS, QS, all are primes. In particular, PIs and QIs, QJs are all prime. All prime. All prime. We can suppose that n is less than or equal to n. Let n is less than or equal to n. Since P1, P2, etc. Pn that equal to Q1, Q2, etc. Qn. We know that P1 divides. We know that P1 divides Q1 and hence P1 divides Q1. P1 divides Q1 for some J1 will be equal to J1 will be equal to J1. So P1 is 1. P1 is 1 equal to Qi Sj belongs to R. Next page number 242. 242. They will cut, I think. We'll try. Now, rest you'll do as homework. First part, we'll do. We'll cut the screen. Right.